The theory predicts that where there should have been no elements and isotopes according to the classical liquid drop model of the nucleus, and taking into account the effect of nuclear shells, some islands of stability appear where the lifetime of nuclei significantly increases. If we leave the island here, then it is 10 to the power of -6 seconds, microseconds, milliseconds, seconds, thousands of seconds, 10 days, 100 years. This indicates the sharp increase in lifetime. And here, the nucleus undergoes mainly alpha decays. It is still relatively stable in relation to spontaneous fission, the zone of which is shown in green on the map. Now we are trying to reach this area by using calcium-48 and a target of heavy actinide isotopes, essentially moving away from what our predecessors did when lead and the heavy isotope nickel-64 were used. In this reaction, we obtained element 110, which decayed not once, but twice, before it underwent spontaneous fission. Now we are able to obtain a compound nucleus by taking the heavy isotope of curium, namely curium-248 and calcium-48, resulting in isotope 296. We obtain proton number 116. By the emission of 3 neutrons, we obtain isotope 292, and by the emission of 4 neutrons, isotope 293. And if everything is correct, they will decay. This even-numbered isotope will have 2 alpha decays, and as soon as it touches the green territory, it will undergo spontaneous fission. Due to the prohibition of spontaneous fission resulting from an odd number of neutrons, this chain will be slightly longer. An odd-numbered isotope will experience 1 decay, a second decay, and a third decay, but it will still end in spontaneous fission. Therefore, the picture should look like this: 2 decays, 3 decays, 4 decays, maybe 5 decays occur in succession. As soon as we descend from the island of stability into the sea of instability, spontaneous fission occurs. This is the first and most striking example of the fact that we are moving downwards. In all other cases, we would not have had alpha decays taking place first, followed by spontaneous fission. One event appears here that I would like to draw your attention to. If we see this picture, we can check it by changing the target. Since alpha decay is taking place here by taking a target that has exactly 2 protons and 2 neutrons less than at the beginning of the process, for example, using plutonium-244 instead of curium-248 plus calcium-48, then we will fall exactly 1 step lower. If we keep all other conditions unchanged, then we should see these steps, starting from this mother nucleus with atomic number 114. That is, we change only the targets, leaving the calcium-48 particle. If we want to climb 1 step higher, we can return along the same stairs. Or we can also do the opposite, take a target that is 1 step lower, and then we will descend in the same way as the nucleus descended after it experienced the first alpha decay. This is an essential factor for identifying these nuclei because this chain is not ideal when we have the first decay, the second decay, and then spontaneous fission. The chain is completely cut off from the area of known nuclei. I will discuss this topic in more detail later. The old, well-known method that was used by Madame Curie, in which the daughter nucleus is identified before the first decay takes place, followed by the second decay and then decaying into another known nucleus, is simply not applicable here, because everything comes to a stop at spontaneous fission before we reach the known territories. This entire process takes place in unknown regions. This is a very important point that always makes us doubt whether this is really what we are seeing. The first experiment was carried out in 1998, after cold fusion experiments were completed in Darmstadt, and then the heaviest nucleus was obtained, that of element 112, with 165 neutrons and a mass of 277. The lifetime of the element is insanely small, at only 0.7 milliseconds, but it lives. The heaviest isotope of element 110 has 163 neutrons. Its lifetime is even shorter, 170 microseconds, but it also lives on a nuclear scale. We must correctly understand that the fact that they exist at all is already a lot. This is because they are located near a closed shell of 108 protons and a closed shell of 160 neutrons. This is the so-called deformed nucleus, a deformed shell. These nuclei are not spherical but deformed. They exist but have very short lifetimes. When we talk about a distant island of stability, where there is a spherical shell and where the number of protons should be 114, and the number of neutrons should be 184, this shell does not affect these nuclei in any way. If we continue in the same direction, we would simply plunge into the sea of instability, all the while reducing the half-life until we reach the limit of sensitivity. We can now enter this area, which was previously inaccessible, using targets made of plutonium-244, curium-248, and calcium-48. And these decay chains that I have shown you were first discovered in the year 2000. First, plutonium-244 was created. As we have seen, it started with one alpha decay, followed by spontaneous fission, and the second chain had two alpha decays, followed again by spontaneous fission. When we climbed a step higher and obtained element 116, we saw that after the first alpha decay, we were going in approximately the same direction. It would be interesting to see what the lifetimes of these decays are. Take element 110 as an example, and we can move along this horizontal line. That was the heaviest isotope at 170 microseconds, traveling 1, 2, 3, 4, up to 11 seconds. The difference is 5 orders of magnitude. Let's go up one step, looking at element 112 at 0.7 milliseconds, and here we go again, traveling up to half a minute. Another 5 orders of magnitude. Well, on the left side, there was no lifetime for element 114, but here we have the lifetime on the right, which was obtained, and it lives for 2.5 seconds, quite a perceptible time. And finally, element 116, 60 milliseconds, and its lifetime was the first obvious indicator which showed that movement in this direction, in the region of a large number of neutrons, significantly increases the stability of the nucleus.